Energy is the ability to do work. And we already talked about two types of energy, kinetic and potential energy. Today we're talking about energy conservation, which says that the total amount of energy stays the same. Now this includes both mechanical and non-mechanical forms. Mechanical forms are what we had already talked about. Kinetic, which is the energy of motion, and potential, which is the energy due to an object's position. Non-mechanical forms would be things like sound and light. Those are a lot of times the two most common. And so energy is conserved. All forms of energy are conserved regardless. However, mechanical energy, which is only the kinetic and potential, is conserved only when there is no friction. So think of it this way. Let's say we have a roller coaster with two different size hills. And so the roller coaster car starts here, and at first it only has the potential energy due to being high up. So let's just say it has 100 joules. That's an absurdly low number, but just for the ease of calculations, let's say that it has 100 joules of potential energy. It is not moving at first, so it starts with 0 joules of kinetic energy. Now, as the car gets to the bottom of the track, what happens is that it loses all of its potential energy, because now it has no position above 0 height. So again, potential energy, gravitational potential energy, is the potential energy being above or below a 0 height. So since we're at 0 height, has no potential energy. So all that potential energy turns into kinetic energy. So the kinetic energy goes up by 100 joules. The total must stay the same. In other words, energy is simply transferred from one form to another. So the potential energy that's lost goes into the gain in the kinetic. Now let's say it gets to the top of this next hill. So here it's moving. And now we get to the top of this next hill, and it's still moving. Not quite so fast though. What happens is it's gained a little bit of potential energy back, because now it's been raised again. So raising an object up makes it gain potential energy. And so now let's say it has gained 40 joules of potential energy. So how much kinetic energy must it have? Well, remember, the total must stay 100. And so if it's gained 40, there is 60 joules remaining that must be kinetic energy. Now this is under ideal situations when there is no friction. But what happens in real life? Well, in real life there is friction. And so we have to consider energy that goes into heat and sound. And so at first, the car is not moved. There's no heat or sound. Now in real life, if it loses all of its potential energy as it gets to the bottom of the first hill, that does not mean in real life that the kinetic is really 100 joules. Let's say that it's only 80 joules. Where did that extra 20 go? Well, it went into non-mechanical forms such as heat and sound due to friction. And it's important to point out here that friction is not a form of energy. Friction causes heat and heat and sound would be your forms of energy. So our total is still 100 in real life. It's just that some of that has gone into non-mechanical forms. And so let's say now as we get to the top of the second hill, we are not really at 60 joules of kinetic energy. Maybe we're only 30. So again, we're only at a total of 70, we must be at a total of 100. So where did that extra 30 joules go? It went into non-mechanical forms, such as heat and sound. So the total must always add up to 100. The total must always be the same in any situation. It's just that under ideal circumstances, however much potential gets lost, that's how much kinetic is gained. But in real life, what happens is however much potential is lost, it goes into both kinetic and also non-mechanical forms such as heat and sound. To demonstrate conservation of energy, we want to look at a pendulum here. So it's just a mass on a string, and what I'm going to do is pull this pendulum over to the side and I'll put this against my chin. Now, as I let go of this pendulum, it's going to swing over and back. And I don't have to worry about the pendulum hitting me back in the chin, because if it were to come higher than I originally released it, that would have meant that it has gained energy more than what it started with. And that's impossible according to conservation of energy. And so if I let this go, let's say it starts with 100 joules here, that 100 joules gets turned into kinetic at the bottom. So here we have 100 joules of potential, let's say. Now that potential loses and becomes kinetic. So now we only have, 0 joules of potential, and we have 100 joules of kinetic. But now as it gets back over here, we lose that kinetic and gain it in potential. So now we have 0 kinetic energy, but we have 100 back in potential. Now it goes back down here, where it loses all its potential, and now we have 100 joules of kinetic. And then it comes back here, and we have now lost all that kinetic and gained 100 joules of potential. But what you'll notice is that in real life, it doesn't actually get back to the same height at which it started. And the reason is because some of that energy goes into non-mechanical forms due to the friction up here at the top, where the pendulum is connected to the ceiling. And so some of that energy goes into our non-mechanical forms, such as heat and a little bit of sound. Not much, but it loses some. And so therefore it never even gets back to the same height at which it started. Finally, as a test of your knowledge, what I'd like you to do is make a prediction. I have 3 tracks here. The first track dips down a little bit and then is straight all the way across. The second track in the middle is going to dip down all the way, and then there's a hill in the middle. And the third track dips down all the way and then goes all the way across before it comes back up. I have 3 identical objects, 3 identical balls, and I'm going to release each one from the top of this side of the track. What I want you to do is predict which one will go over and back first. So go ahead and pause the video, take a little bit of time, and write down your predictions. Okay, so let's test that out. We'll release it from each track. And we see that the track that went down all the way is the one that got back first. So again, what I'd like you to do is pause the video, write down your explanation as to why you think that the object that went down all the way, the track that went down all the way, is the one in which the ball came back first. So the explanation here is that, remember, we're starting with the same amount of potential energy for each object. And so when that object goes down, it loses the potential energy, which turns into kinetic. Now the one on the far end, the first track, has lost the least amount of potential, and therefore gained the least amount of kinetic. Remember, kinetic energy is the energy of motion. So because this one has lost the least amount of potential, it has gained the least amount of kinetic, and therefore moves the slowest. These 2 objects lose the same amount of potential as they go down the first hill. And so therefore they gain the same amount of kinetic. So they are moving at the same speed. They're neck and neck, side by side, until we get to this point. At this point, this one with the hill is going to lose the kinetic as it gains potential. So it loses speed, just like a speed bump. It slows you down. And so as it gains potential, it loses kinetic and therefore loses speed, while this one continues at the same kinetic or same speed and passes it by. So again, conservation of energy, however much potential you lose, turns into kinetic energy. Under ideal situations, meaning there's no friction, the amount of potential that's lost is equal to the amount of kinetic that's gained. But under real life situations, when there is friction, the amount of potential energy that is lost turns not only into kinetic, but it also might turn into non-mechanical forms such as heat and sound. So I hope you learned something from the video, and make sure you write down any questions that you may have so you can ask them